Hey guys, and welcome to Circuits. So today we're going to kick things off again in electricity, but talking about circuits. So current electricity instead of static electricity. So we know that electrical energy, electrons, can be transferred by the movement of electric charge, right? We've seen that happen. Lightning can jump. We got sparked a bunch last week. It was awesome. Now, the movement or flow of electric charges from one place to another in a controlled manner is called an electric current. So last week it was static electricity. Static electricity is electricity that doesn't move much. This week we're looking at current electricity, electric current. Current, you think like current in a river, right? It flows. Electricity that moves. So when electrons are moving or flowing from one place to another and we can kind of control it, we call that electric current. So you can see in this fancy little diagram here, this would be a wire that you zoomed way in on, and you can see the electrons moving. Now, they don't all move in a straight line. Really, they're zigging and zagging all over the place as they bounce their way through and hit a bunch of protons and stuff. But they move generally in the same direction because they're being repelled from one side and attracted to the other. Very similar to how we did our static electricity stuff. So although we introduced lightning in static electricity, that's technically movement, right? So the movement of charge during a lightning strike indicates, isn't lightning a form of current electricity? Well, the big difference between current in a lightning strike and what we would consider more like a static electricity where it just kind of jumps somewhere, like we would consider flowing, if it's flowing through a light bulb, for example, in a flashlight, we call that current electricity. And it's because the current, the electricity that's moving, has a controlled path. So we can set up a controlled path and we call those paths electric circuits. So if it's uncontrolled, if it's a spark or lightning or a zap or it's not moving very much, that's kind of all under the field of static electricity. If it's moving and we can control it, it's in a circuit, for example, then it's in the field of current electricity. Some people don't really like calling it static and current electricity because it's all the same stuff. It's all moving electrons. It's all just electricity. So an electric circuit is just a continuous path in which electrons can flow. So if you ever looked at a battery, you'll see that it has a negative side and a positive side. And if you remember anything about electricity, negatives would repel negatives, right? So you would get electrons being repelled down this wire. It goes up into your bulb, through your other wire, and then it's attracted to the positive side. So as long as that battery keeps having a negative side and a positive side, it'll keep pushing electrons in the same direction. That gives us a current. So we use these electric circuits to convert the electrical energy, convert the electrons moving. We want to take those electrons moving, turn their energy into other forms of energy. We need moving electrons to turn into something useful, turn it into light, turn it into heat, turn it into movement like a motor. So, getting shocked is fun and all, but it's not going to turn your iPad on, right? So we need to change moving electrons into something useful, and that's what circuits do. So let's take a look here. Our big focus is going to be on electric circuits today. So let's look at the different parts of a circuit. All circuits need to have at least three basic things. A circuit will not work unless it's got these three. One, a source. You need some kind of device that creates electrical energy from something. So sometimes we use chemicals. That would be a battery. So inside your battery is a bunch of chemicals that spit out electrons, and the electrons are repelled from one side and attracted to the other. Sometimes we can create electricity mechanically. So we can actually use a hydro dam, for example, to generate electricity. We're going to talk more about that in a future lesson. We can also use solar power. Sunlight comes in, hits these what are called photovoltaic cells, and it's a special material that when light hits it, it actually knocks an electron loose. And the electron goes down through a wire, and we can use that electron then to charge things. So solar panels are a very special material that light can generate electricity from them. And so we use all different things to be a source of our electrons. Most commonly would probably be the battery for what we do in school. But if you plug into the wall, you're probably using energy from a hydroelectric dam. So a circuit's only going to do us work, do some good, if we put what's called a load on it. And a load is what uses your energy, right? If I just hook a wire up to a battery, whoop-de-dee-doo, nothing's going to happen, right? That's not exciting. So we put something on the circuit, we put a load on it to actually do something. So these loads resist the flow of current. They kind of block the electrons from traveling as well. And as part of blocking it, it ends up turning that energy into a form that we need. Sometimes it turns it into heat, like in a toaster. Sometimes it turns it into light, like a light bulb. Sometimes it turns it into sound energy, like a speaker. Sometimes it just turns it into movement, like a motor. So these are all things that we can do. So the electrons come through here into the motor, and as they bump around inside this motor, it's designed in such a way that the electrons traveling cause something inside the motor to spin. And then they come out the other side. And we'll probably talk more about those designs later as well. It's actually really quite interesting how that works. But so we can use the electricity only if we have a load. If there is no load on your wire, it's useless. You're not really having a circuit. You're not controlling anything because nothing's happening. The last thing you need, of course, is a path. I can't just put a battery on the ground and put a light bulb beside it and be like, woohoo, it's going to work. You need to connect stuff together, right? I mean, you guys know that. That's pretty basic. If things aren't plugged in, they don't work. So the path is not necessarily what we might consider normal conductors, like metal or wires. It could also be water, ionized air. You can even stick a frog in there and it's going to work. Anything that conducts electricity could be considered a path or part of your circuit. Now, to be fair, normally we use wires because they're easy to control. They're not dangerous. They're quite safe. Normally, we don't just stick frogs in between our computer and the socket and hope that it's going to charge well. A, that would be really bad for the frog, and B, it'd probably be bad for our computer. But when we talk about an electric circuit, our path is almost always going to be, again, the conductor, the wire. So why do we need it? Well, we need a way to actually move the electrons, to transmit the electrons from the source anode. Anode is fancy science speak for the negative side. To the load. So you got to go from the negative side to your light bulb, your motor, whatever, to your load, and then back to the source cathode. Oh, I don't have to write that down. It's already in here. Negative terminal. Cathode is positive terminal. So if you're ever talking about batteries, it's kind of chemistry related. In chemistry, we love cats. Cats are positive. So if you're ever thinking, oh, what is a cathode? What's the anode again? Cats are a good thing. We love cats in chemistry. So cathodes are the positive side. Pet fans here. Now, there is a fourth component that a lot of circuits have, almost all of them. Now, it's optional because it's not necessary, but they're very helpful. Some way to control the electricity. I mean, it's great that your light bulb's on and all, but it'd be really cool if we could turn it off sometimes. So we use a switch to limit the flow of electricity. We can pick when we turn it on and when we turn it off. It's a way of controlling the circuit. Now, it doesn't have to be a switch. There are other options. The switch is the most popular, but an example would be your thermostat. It allows current to flow based on the temperature. You can use a timer. At a certain time, things connect and electricity starts to flow. Use it to warm up your car in the morning, right? There's different ways of controlling when electricity goes. All of them do the same thing, though. They either make or break a path for the electrons to flow. So if you look at a switch, we call this an open switch because it is open, not closed, not connected. And if it's open, electrons come in one side, go up, and they're stuck. Electricity can't flow through the switch. The path's not complete. The light bulb doesn't light. Nothing happens. If I close the switch, though, electrons can go all the way through and out the other side. Your circuit's complete. Electrons flow. The light bulb lights, and life is good. So how do we draw these things? You can describe a circuit with words, right? I can tell you, take a battery, hook it up to a bulb, and put a switch on there somewhere. But it's often much easier to represent things with symbols, especially when they get big and complicated. You want to look at like the circuit diagram of a computer, it'll blow your mind. You wouldn't be able to draw that. You definitely wouldn't be able to describe it with words. So when illustrating simple circuits, there's a universal method for drawing them. That means you go anywhere in the world, these drawings are standardized. They're taught all across the world. Even in places that don't speak English, they use the same symbols, the same things to illustrate these circuits. Now, these are called schematics, also known as circuit diagrams. Excuse my messy writing. So schematics or circuit diagrams. So how do we draw a source of electricity? It's just like this. That's called a cell. A cell generates electricity. That means this is where you get electricity from. It converts stored energy in some form, usually like a battery, into potential energy, and it allows current to flow. So if I want to connect this to itself with a wire, comes out one side, comes in the other side, life is good. Now, how do I know what side is which? The short side is less. The big side is more, negative and positive, right? More is always better. The bigger side is positive. The smaller side is negative when you have a cell. Now, batteries, the ones you use, are more than one cell. Batteries take a bunch of cells and smash them together to get a little bit more power. So you'd see a battery would be like a 3-cell battery has 3 sets of long and short lines. But the rules are the same. Long side is positive, short side is negative. It would just be 3 times as powerful as a single cell. So it's more often than not, if you're going to write a battery, usually you use a set of 3 lines. You could put a couple more, you could put a couple less, unless the question specifically says like, hey, you draw me a 3-cell battery? As long as you draw a few in there, you've got yourself a cell. Big line, small line, big line, small line, that's your battery. All right, so we got a source of energy now. What are we going to connect it to? What do the loads look like? 2 options for a light bulb. You can draw it as a circle with an X through it, or a circle with, well, it looks kind of like a butt. I usually draw it like this because I'm lazy. It looks less like a butt as well, so I'll take that. But so when you draw it this way, this is what a bulb looks like. Any of these 3 really will work. And so these are light bulbs. You want to put one of these on a circuit, you'd be good to go. Used to determine if electricity is flowing. I mean, it's also used to light a room, right? That's probably the more important one. But if you were curious if electricity was flowing, you could always put a light bulb on there and see if it lit up. So we have other options, though. Sometimes we don't want too many electrons flowing. Like if you were to take your cell phone, for example, and plug it directly into the wall, it would probably explode. All your cell phone chargers have that little brick thing, right? Sometimes the wire comes out of the brick and the brick plugs into the wall. Sometimes on stuff like laptops, the brick's halfway up the cable. But that brick's job is to regulate how much current actually flows. I don't want too many electrons going into this device. It's too small. Can't handle it. The wires aren't built for it. So how do we slow down electricity? We use something called a resistor. Its job is literally just to get in the way. Just slow it on down. It'd be like if I stood in the hallway and just pushed everyone that came by. All I'm doing is standing there slowing down the flow of people walking through the hallway. Nobody can get past me. I'm just going to give you a shove. I'm not going to stop you. You're going to get by, but if you get them close, I'll give you a little push. And that's going to slow down the flow of everyone trying to get to class, right? So resistors control the flow of current to other components so they don't get too much electricity. You can use them to limit the amount of current if you want. If you put way too much current through, the resistors actually get so hot they're destroyed, which sounds terrible. But if, let's say I got my cell phone plugged in and my house gets hit by lightning and a bunch of it goes into my cord, I do not want lightning coming out of my cell phone, right? That would destroy my cell phone. But if the resistor in the brick gets destroyed first, then there's no path for electrons to flow. The rest of that lightning can't get into my phone and fry it. It actually protects the circuit. So resistors can be used as a form of protection. We have other better ways to protect things. Circuit or resistors would be like a last minute kind of thing, but it is something we use to limit current, protect the devices that are on a circuit, and make sure not too much gets through. Oh, and it's drawn like a squiggly line. A fuse. Now the fuses are the main source of protection. It's literally just a box that you put your wire through. Its job is basically to prevent fires, really. If there's too much current going through, the fuses will separate and stop electricity from flowing. And that's all they're designed to do. They don't slow down the flow of electricity at all, But if there becomes too much electricity, it stops it cold. So an example of a fuse would be like in your house, those breakers, you put too much electricity through, you plug in too many things, you turn on too much stuff, and then all the lights in the house turn out. Those breakers have a fuse in it. So it's almost like a spring-loaded thing. And when it gets too hot, when too much electron gets through, the metal gets soft and snaps. Where's my eraser? Book. And flicks up into the air because of the spring. And then electricity can't flow anymore. And you got to go down, take that switch, and reset your breaker. And then you're back to normal current again. So fuses are a way to protect your circuit. They basically stop electricity from flowing if too much current goes through. So we've got a source. We've got a load. Last thing you need is a way to get it around. And literally for wires, we just use a straight line. Carries the flow of electrons, creates a path to connect different parts of a circuit, and everything does need to be connected. So if I wanted to connect, I don't know, let's just say I had a resistor hooked up to a battery. There we go. Make that a little bigger. So I want these things to work together. I'd have to take a wire from my positive end to the resistor, and then from the resistor to the negative end. And again, electrons are repelled from your negative side. So I would see electrons flowing through my resistor and back into the battery. And they would keep flowing and flowing and flowing until that battery runs out of juice. So this resistor would just slow down the electrons so they don't go too fast. Another thing I can do sometimes is I can ground charges. So this is to prevent an electrical shock. If you see more complicated circuits, they will sometimes have a ground wire attached. And basically, so you see, hey, here's my circuit, battery, yoink, goes to my resistor. And if I was worried about something in the resistor going wrong, maybe that resistor has a grounding wire attached. So that just said, if something happens with that resistor, if that resistor breaks or goes bad or something in it is wired up, then the electrons can go to the ground. I've provided it a safe outlet. That way, if something goes wrong and I go to grab the light bulb or the resistor, I don't get a shock, right? If it's not working quite right, the extra electricity can go to the ground and I don't get shocked, which is a good thing. We don't want shocks, especially if it's coming from our walls. So it directs your electricity into the ground, prevents electricity from flowing in a different way. If you build up enough electricity, it'll flow through whatever it can find. And often that starts fires and burns houses down. So a lot of things these days are grounded to keep things safe. Lastly, how do we control this flow? You put a switch on a wire. So here's my wire. There's a closed switch. Electricity can flow. Here's my wire. Yoink. There's an open switch. Electricity can't flow. You literally show a break in the wire. So it allows the flow of electricity to be turned off and on. Often if they ask you to put a switch in a diagram, they want to see it open. I mean, everyone knows you could close it if you wanted to. It's just easier to see if it's open. Putting a couple little dots on a line doesn't make it very easy to see. So this is the better way to draw a switch. Do it open. So here it is. Pause. Your turn. I've been talking for way too long. Pause this video. Draw this circuit. So here's the picture. You got a battery. This is supposed to be a switch. I'm going to label that. It's a sketchy switch. So a battery leads to a switch, leads to two different light bulbs, and back to the battery. Pause it. Use the circuit symbols you just learned. Sketch it. All right, if you're back, this is good. You've drawn this circuit, I hope. What I want you to do now is take that, show it to your teacher. If you're at school, anyways. If you're at home, you might not have much luck, but pause it again. Go show your teacher what you got so they can confirm that you know what you're doing with circuits. That would be a good plan. For you at home, people, here's your battery. There's a switch. There's my two bulbs. Should look something like this. So now that we can draw circuits, great job, everybody. We're going to look at different kinds of circuits. There's only two we're going to look at today, then we're going to wrap things up. Won't be much longer here. We got series and parallel circuits. So these are the two main kinds of circuits we're going to look at. So we can actually connect these wires and these components, these lights, these bulbs, whatever, in a whole bunch of different ways. And the two easiest ones are series and parallel, and we use these all the time. A component connected in series are connected along a single path. That one you just drew was a series circuit. The same current flows through all the components. If my electron leaves this end here, it has to go through the switch, through this bulb, and through this bulb. Every electron flows through every component. That's the only option. The other circuit you can draw is a parallel circuit. Now, these things are connected so that the same voltage is applied to each component. So the way this works, let's say this was a 9-volt battery. This would take up 4.5 volts of push. This bulb would take up 4.5 volts of push. Each of them takes a certain amount of charge to actually work. If you were to hook things up in parallel, though, so instead of having one path, my electrons flow this way or this way. Both of these, like this wire here is at the 9-volt level. This wire over here is at 0 volts. Both of these bulbs would see 9 volts, which means your battery will actually drain a little bit faster. But you got two bulbs getting more energy. So those are the two kinds. One has a single path. They have to split the voltage. One, you have multiple paths. So if I have an electron going, it gets to choose which bulb it goes through. It doesn't go through both. So your bulbs get more power. But what if we did batteries in series? What if I took a battery and instead of hooking it up to a switch or something else, I hooked it up to another battery right away? We doubled up on the batteries. All right. If you connect batteries in series, you double the voltage. So if this is a 9-volt battery and this is a 9-volt battery, this resistor is getting 18 volts now. That's a lot more energy going through that battery. But here's the thing. You maintain the same capacity rating. That is basically how long your batteries last. So if one battery lasts 1 hour, then 15 batteries connected in series still lasts 1 hour. You can put up 1 billion batteries in series. I don't care. It's only going to last an hour. It doesn't change how long your batteries last. You get more power, you don't get more charge. So you get, this can be handy. Your light bulbs glow brighter. Your motors run faster. You look at like the Tesla car. You better believe they got a lot of batteries in series there because they want to spin those motors fast. But their batteries won't last as long when they do that. If you connect batteries in parallel, well, so here's my battery 1. Let's look what that looks like. Here's my resistor. Here's battery 2. There we go. So they're both pushing the same kind of direction. What happens is the battery life gets doubled. Twice the life, which is fantastic for your cell phones and your vehicles, but you have the same voltage. That's a 9-volt battery. That's a 9-volt battery. This thing only gets 9 volts. So you don't get any extra power out of it. So if you were to look at things like a laptop battery, you want more energy. So you put your batteries all in parallel. It makes your laptop last longer. Same with your cell phone. If you were to look at a car, maybe they put enough batteries in series to get the power they want, and then make a whole bunch of these cells in parallel. So I've got the amount of power I want. Now I'm going to do this in parallel. Enough times that I get more battery life. So let's do an example. This is 3 volts, 3 volts. All these batteries are 3 volts. Seems like a lot of voltage in this circuit. What would your resistor have? How many volts would go through this resistor? Well, this set of series totals 9 volts because the volts add. This set of series is 9 volts. This set of series is 9 volts. And because they're all parallel to each other, you'd only have 9 volts going through your actual resistor. But your battery would last 3 times as long as this 9 volts itself because I have 3 parallel sets. So you can put these ideas together to figure out how much power and how much battery life I want by just cramming more batteries in. That's why cell phones keep getting bigger and bigger. You need to put more batteries inside it to make it last longer. What about bulbs, right? So we talked about this a little bit. Here's bulb 1, here's bulb 2. We're both in series. If they're in series, the current has to go through every single bulb. Ugh, so much work. What this means is that the resistance of the circuit gets higher with every bulb you add. The more bulbs you put in there, the slower the slower the current is gonna flow, which means the less each one is going to glow. The more bulbs you put in, the less bright they glow, as they have to split the energy up. So by removing a single bulb, you'd actually break the circuit too. So if I took this bulb out, well, there's now a hole in my circuit, which means this light goes out and energy stops flowing. Electrons can't go in a circle because there is no circle. I got rid of my bulb. So you do have to be careful. You want to keep your bulbs in, or think about Christmas lights, right? You ever had that happen to you? One bulb goes out in the Christmas light and the whole darn string goes dark? That's because a lot of Christmas lights are wired in series. So as soon as one goes bad, the whole string goes out, and you got to figure out which bulb went out. Terrible idea. So how do we fix it? We connect bulbs in parallel. When connecting bulbs in parallel, you're actually adding more pathways for electricity to take. Oh, that's an ugly bulb. Whoopsie. There we go. Now my electrons can go multiple ways. Now, oddly enough, this causes resistance to drop. What that means is that your current is actually going to flow faster. If you had one bulb on here, it's actually going to travel slower than if you had 2 bulbs on here, which seems really weird, but I'll explain to you in a minute why it works that way, and it'll make a little more sense. But as you add bulbs in parallel, because they get the same voltage across them, adding bulbs does not change the brightness at all. I can add as many light bulbs as I want. I can have 400 light bulbs on this one battery. They'll all burn full brightness. It'll be great. But my battery's going to die in 2 seconds. So I get full brightness on every bulb, but your battery drains faster. Twice as fast with 2 bulbs, 3 times as fast with 3 bulbs. So if I actually put 400 bulbs on there, you can imagine how long my battery would last, right? Not a great plan. But the advantage is, if I take a bulb out, I haven't broken the entire circuit. There is still a circle for electrons to flow in here. So that light bulb doesn't go out. Only the one that broke went out. That's the dream, right? I don't want to have to turn off. Imagine if, in order for you to turn off a light bulb in your house, you had to turn off every single thing that used electricity. Either your house is completely lit or your house is completely dark. That is the only option, because as soon as you break one thing, that would be what would happen if your house was wired in series. But we wire most of our houses in parallel. So I can turn off a light bulb or a lamp and not have the entire house go dark. We would do wire some things in series. Like you might notice, like in the classroom, when I hit a light switch, a whole row of lights goes out. All of those lights would be wired in series. But it usually is wired in such a way that the whole building doesn't have to go dark, because that wouldn't make any sense. So it allows you to keep stuff lit because the circuit hasn't been broken if something goes bad. I wish they did this with Christmas lights. So if you're still confused by the fact that electricity flows faster when you have more bulbs, think about cars on a highway. If you have to stop at a toll booth, that's like a resistor. Now, so here's my road. Fantastic. I have great art skills. Here's my toll booth, and my car has to stop. There's my car. Wonderful. Now, that's going to slow down traffic, right? What if I add 2 more toll booths in a row? Now, every car has to stop 3 times. That highway is going to be very, very slow. So here's my other option. Here's my road. Here's my toll booth. Here's my car. Let's add more cars here. They're all lined up. It's a bad traffic jam. They all got to go through every toll booth. They're all honking. They're all hot and sweaty and not happy about being on the road. So here's my second option. I have to add 2 toll booths. So I say, okay, smart guy, I'll add another path, another road we can take, and I'll put a toll booth on there. And I'll do another one on the bottom. Ignore my amazing art skills. There we go. Now if I have 3 cars, they go to 3 different paths. They get through 3 times as fast. If I had 100 cars, which would be faster? Putting 100 cars through 3 stops or putting 100 cars through 3 lanes, right? So you end up getting more cars traveling. If you think about a circuit, you end up getting more electrons traveling. You actually increase the current. You can use more electricity now that you've made more lanes for the electrons to travel down. That's why parallel gets more energy and why the battery dies faster. So here's what we're going to do with this knowledge today. We've learned some stuff. I want you to do just 3 things. Shouldn't take you too long, I hope. You're going to convert the following descriptions into circuit diagrams. First, draw a circuit diagram which contains a battery with 2 cells, 1 pathway with an open switch, and a resistor. Show the direction of electron flow if electricity is flowing. If it's not, you don't have to draw the direction. Is this a series or parallel circuit? Number 2, draw a circuit diagram containing a battery with 3 cells. Big twist. 1 pathway with a closed switch, so you can actually draw the closed switch, and a light bulb. Show the direction of electron flow, again, if electricity is flowing. If it's not, you don't have to draw it. Is this a series or a parallel circuit? And finally, draw a circuit diagram containing a battery with 3 cells, 2 pathways with a light bulb on each, and a switch that could turn off both bulbs at the same, could turn both bulbs on or off at the same time. Show the direction of electron flow. So because your switch could be open or closed, I'll let you choose, but for this one, show the direction no matter what. Is this a series or a parallel circuit? So that's the activity for today. That's the lesson. Hopefully you guys are experts in the current, electricity, and diagrams now. If not, well, come talk to your teacher and we'll figure it out. So thanks for watching, guys, and I'll see you next time.